A bar with two pivots, and it is pretty much asking what is the force of A and the force of B. So what we have to know, well, we know the RF sine theta, but sine theta, the theta is 90 here, so it's just RF pretty much. Those are our torques. So we can do torque or tau. It's going to be our R, right? So we're going to start with this to the center, right? So this fulcrum or pivot, whatever, to the center. And we know that the length of is 1.2, so this whole thing is going to be 0.6. So 0.6 minus 0.3, what is this distance? It's also 0.3, so 0.30. And then RF, so what is the F? Well, it is the mass of the bar times gravity. So 0.3 times 1.50 times 9.81. And then it would be sine 90, but we don't need that because that's just 1. Then that is going to equate to the distance from FA fulcrum to FB pivot, whatever. And what is that? Well, we can just do simple math. If this is 0.3, so 0.6 plus 0.5, so 0.75. So that's what that's going to be, right? Our R, which is, right, FB to this whole thing, that is going to be our R. That is 0.75. Just found that. And that is going to be times the F. Well, what is the F? Well, the F is FB, this force right here, right? So once we have that, we can do a numeric solver, and we can find out to be FB equals 5.89 newtons. So that is how to find FB. Now, how do we find FA? Well, if we think about it, the bar coming down from the mg, right? That force right here, this is mg, and that is going to be equal the force of A pushing up and the force of B pushing up. So these two forces added are going to cancel out this one force coming down. So what can we do? We can do FA plus FB, which is, we just found, 5.89, is going to equal mg, 1.50, right? That's the mass, times 9.81. And we can use solver, and we can get FA equals 8.83 newtons. And that is how to do a bar and pivot question like that. A spring force question, because we see the spring here. And there are two mechanisms set up, and they both have the they're both connected because it's the same spring. And we are asked to find the change in X, the delta X here. So first, let's set up an equation for this too, so that we can, or actually what we can do here is we can start here, the right side, to solve, because spring force equals negative kx, right? In this case, this is y. So our Fs, well, we know it's mg, so 22.0 times 9.81 equals, and then that's the Fs, negative kx. What is x? Well, it's final minus initial. So the final is down here, so it's negative 0.61. So, and remember here, he said the negative k, it doesn't really matter that much. So let's just solve for a k here. Pretty much simple algebra, 22 times 9.81 divided by 0.61. And our k comes out to 354. And the units for k are Newton per meters. So our spring force there, that's pretty much what we solved for, and we solved for the k. So now with this k, it's the same exact case, and it's the same exact spring. So we can try and use it in this mechanism here to find the delta x. So what can we do? Well, let's think about this. Let's put all our forces together. So this is going down this way, and the acceleration is 0 since it's still, it really hasn't gone anywhere. So what we can do is we can set up our spring force. So we know spring force equals negative kx. So our k, we can do 354 times delta x equals the forces pretty much here, the other spring force. So what is this? How do we do this? Well, it's mg sine theta, right? We know all those, so we can do 22.0 times 9.81 times sine 52.0. right? And then what else is acting against this force? Well, it's friction. And how do we solve for friction? Well, we know force of friction equals normal force times mu. And we have all those because we can solve for normal force here. So I don't want to overlap, so we'll just come here. So it's minus friction, which is normal force. What is normal force? mg cos theta, right? So 22.0 times 9.81 cosine 52.0. And we can do numeric solver, and our delta x, let's see, we can go 354, x equals 22 times 9.81 sine 52 minus 22 times 9.81 cosine 52. And we should get our delta x comes out to 0.441 meters. Might have been a little calculator, but yeah. So that is our delta x, and that is how to do a spring force problem like that. Okay, in this centripetal force problem, Ani is in Darsh's car, and Ani feels a force of 67.67 newtons going around this circle, and he weighs 67.67 kilograms, and his velocity is 6.7 meters per second. So this equation, we are tasked to find the radius of this circle he is driving in. So what is the equation? Well, the equation is AC equals V squared over R. So first, we have to find what AC is. So how do we do that? Well, AC, so F, we can use Newton's second law, F equals MA, and A is AC in this scenario. And so force equals MA, and what do we do? Just divide by M to get force over mass equals AC. And now we can just plug in our force and mass that Ani feels and is. So this is 67.67 newtons over his weight, 67.67. And that is going to equal, well, this is just one. So AC is 1.000 meters per second squared. And we have to find the radius, and so we can plug in 1.000 equals V squared. Well, what is V squared? 6.7 squared over R. And what can we do? Algebraic rules, we can just flip these two to get R equals 6.7 squared over 1.000. And let's plug that in. 6.7 divided by 6.7 squared divided by 1 is just R equals 44.9 meters. So R equals 44.9 meters. And that is how we do a centripetal force problem. Okay, the next question asks a 100 kilogram white totaled Mercedes-Benz, tragic, is at an altitude of 2 times 10 to the 6 meters from the surface of the Earth. Find the change in potential energy, or delta U, and mass of Earth is given and radius of Earth is given. So this question is pretty much testing the U, delta U, which is going to be equals negative G M E times the M of the thing. In this case, it's the Mercedes-Benz, so we'll just do MM, and then it is over the radius, right, whichever one it is. And since it's delta, it's final minus initial. So U final, U initial. And then, yeah, you just subtract them. So we find what the radius at the final is and the radius in the beginning. So what can we do? We just plug the numbers in. So to first, we can do negative, right, because that's negative 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the 24, times our Mercedes-Benz, 100 kilograms, all over our radius final. Well, what is our radius final? It is going to be the radius of the Earth plus the altitude. So what is the radius of the Earth? 6.371 times 10 to the 6 plus radius or altitude, 2.00 times 10 to the 6, right? That is our first, that is final, and that is going to be subtracted by the initial, which is negative 6.67 times 10 to the negative 11 times, again, 5.97 times 10 to the 24. These stay the same, times 100, right? Over, now this is where it's different, it's a different r. And the r is just the radius of the Earth, because at the initial, right, and then the car is here. So this is the altitude, we can do height, and this is the radius of the Earth. So final is all of that, initial is just this. So this is going to be 6.371 times, that's bad, sorry, 6.371 times 10 to the 6, and we can do this minus this, and you should come out to a delta U equals 1.49 times 10 to the 9 joules. And that is how to do a question like that.